So today I'm going to walk you through making some portfolio notes for our atoms unit. So I'm going to write, whoops, make this a little smaller. I'm going to write atoms unit on the top of my paper. So the first thing we want to think about is we have protons, neutrons, and electrons. Well, first of all, what is an atom? So I'm going to say an atom, I'm going to define it, is the smallest particle of an element that retains its properties. Now, while we're on that subject, an element, let's make a little element here. We can have our little element square. So we could say hydrogen, and it has a 1.01, and then we have a 1 here. So we have, this is our atomic number. And the atomic number is defined by the number of protons. So as a little visual to think about this, I think about a little like an ID card, like a driver's license, and it has a picture right here, a picture of the person. And so I could say, whoops, I could say, my thing isn't working. I could say ID card. And on here, up in the, where I would have the picture, I'm just gonna actually draw some little protons, little positive protons, to remind me that it's protons. Protons determine identity. Of an element. So you can have different numbers of electrons and different number of neutrons, but the protons determine the identity. So this is my atomic symbol for the element, and this is my atomic mass. Now, when we're thinking about mass, we always want to round the mass when we're using using the mass in, like, for ape man. So I'm going to write M as sort of rounded. M minus A equals N, and this I'm going to say is the rounded mass. It's just a little visual to help us think about that we round the mass when we're using man, ape man. So mass minus atomic number equals neutrons. Now let's remember that neutrons are neutral. They're in, so if I can't seem to get a different color here. Let me see if I can find another color. If I have protons are positive in the nucleus of an atom, and then if I have my neutrons are also in the nucleus and they are neutral, remember? So neutrons are neutral. They have no charge, right? And then protons are positive protons. So remember, for ape man, we have atomic number equals protons equals electrons. Now the electrons, remember, they're just moving around, right? They're moving around, and they're in the orbitals. Electrons are negative, and they're in orbitals. So in order to think about where the mass of the atom comes from, I'm going to draw, because I want to have lots of pictures in my notes, I'm going to draw a little box here. So I'm going to say if I have an atom, it has 4 AMU, that's atomic mass units. That's how we measure mass. Then all of the mass of an atom is basically coming from those protons, right? I would have 2 protons, maybe if I have a 4 AMU, and I have then my neutrons. So we can visualize four protons. Oops, no, sorry. 2 protons plus 2 neutrons to give us 4 AMU. So that's where our mass comes from. So our mass, and that's why it has to be rounded when we use it, because we can't have part of a neutron or a proton. The decimal in the mass comes from having a, it's an average of all of the different isotopes of that atom. So sometimes we might have a different one. So if we want to think about isotopes, we could go, okay, so if you have, for example, if we have, say we have carbon, and carbon, we have carbon 12. So carbon 12 would have 6 protons, because carbon has 6 protons. But then carbon 12 is also going to have 1, 2, 3, 4, 5, 6 neutrons. So it's going to have 6 protons and 6 neutrons to give a total of 12. And about 99% of all of the carbon in the world is like this, is carbon 12. But some elements of carbon, or some atoms of carbon, have different number of neutrons, and these are what we call isotopes. And so when we look at carbon, we have 12.01 typically as written on the periodic table for the mass. That's because in about one out of every 100 has not 6 but 7 neutrons. 7 neutrons and 6 protons. And this is about 1% of all the carbon in the world. So when we average out 99 12s and 1 13, so this is carbon 13, then that's where we get that 12.01 mass that you see on the periodic table. So I'm just going to put this on here. This teaches me about isotopes. That's our main topic for this section here. Isotopes. It helps us to understand what an isotope is. So I'm going to draw that on there. Okay, so now I want to think about, I've got a good idea about atoms. Now I want to think about the periodic table. So I'm just going to sketch out a little periodic table just for fun. And I'm going to make it like this. I'm going to put, I've got this up here. I'm going to imagine this going down about 2 blocks, and I'm going to go across like this. This line is going to go up to be even to that one. It's going to go over a section, and then up one more and down. It doesn't matter if it's exact. I'm just kind of drawing a rough outline. So now let's think about our let's get some colors here. Okay, so I'm going to talk about this period right here. So I'm going to color this in, and this is I'm going to label my noble gases. And it has 8 valence electrons, and it is stable. Then right next to it, I'm going to have I'm having some trouble here. Let's see. Right next to it, I'm going to have this group here, and this is the halogens, and they have 7 valence electrons, and they are very reactive. Right? Now, let's go over to the other side and think about this group right here. These are my alkali metals. They have 1 valence electron, and they are very reactive. And right next to them, I've got, let's see, this group right here. These are my alkali earth metals. They have 2 valence electrons, and they are also very reactive. So when I'm thinking about the periodic table, I'm also going to draw down the side because I want to remember what the periods tell me. So I'm going to draw my little bullseyes because this visual helps me remember. It doesn't have to be exact. I'm drawing lots of circles. Now, I'm going to remember that everything in this period has this number of orbitals. So I'm going to write a period reads like a sentence. And a group hangs together. And so also this is also called family, group or family. And remember, I'm going to say that families look alike. So here I'm drawing a little family, 2 little people, and they look alike. They look alike. So then if I want to think about now my, what are my metals and nonmetals? So if I have my line here on the periodic table, I'm going to know that these are basically metals. And on the other side, I'm going to have these here, and hydrogen are my nonmetals. And in the middle, of course, we have our semimetals or metalloids. Semimetals or metalloids. And they have properties, metalloids. They have properties of metals and nonmetals. So let's think about what we know about valence electrons, because that's a really important thing. So the valence electrons, oops, let me get a, valence electrons, they are what determine the properties of the elements. So when we talk about properties, what are we talking about? We're talking about its reactivity, boiling point, melting point, color, so physical properties like color and texture and density. We could also be talking about how well it heats up. It's called specific heat. So valence electrons determine the properties of an element. Okay, and I'm going to add in, I was just thinking about protons and electrons up here. I also want to put up here, I'm going to draw a little thing with a proton and a neutron up here, that they are about the same size, like on a balance. But then if I have them on if I have a proton and an electron, then they are very different in size. So I want to put that, I'm going to have an electron up here because it's really little. It's like a little speck. And my proton then would be a lot larger. So protons and neutrons are about the same size, and protons and electrons, electron is much smaller. So we could say electrons are tiny, tiny, tiny. Okay, I'm moving on to the next page now. So I want to go back to valence electrons and add a little bit more about valence electrons. So valence electrons are really important. They are the electrons in the outer shell. So if I have an atom that has the nucleus in the middle, and I have this, if it has two shells, then the valence electrons will be the ones in the outer shell. If it has four shells, then however many electrons it has in the outer shell are where the valence electrons are. That's the valence electrons. So it's the valence electrons that do the bonding when we are looking at chemical formulas, and they do bonding in the compounds or molecules. So the valence electrons are really important, and like we said before, they determine the properties of the atom. Now to count up the valence electrons, while we're on it, I'm going to draw my little pretend periodic table again, and I'm going to write how we find them. So we count up on the periodic table like this: 1, 2, and then I'm going to remind myself that we skip this section in here, which is called the transition metals. So I'm going to go like this, and I'm going to write skip right there, and then I'm going to carry on with the rest of my counting: 3, 4, 5, 6, 7, 8, and that's the number of valence electrons: 5, 6, 7, 8. So that's how we're going to find them. Now when valence electrons combine, when they follow the octet rule. The octet rule tells us that atoms want, we say that they want them, but it's the most stable with 8 valence electrons. And I'm going to draw a little octopus here, I think. 1, 2, 3, 4, 5, 6, 7 with 8 legs, to remind me of the octet rule, that they combine to make 8. So if I have an atom with 2 valence electrons, would probably easily combine with an atom with with 6 valence electrons to make 8. And that's simplifying things, but that can certainly happen. So we find things from period 2 combining with atoms from period 6 easily because it makes 8. So, and so on. Now, let's think about, I want to put a couple things about chemical reactions. So we know that the law of conservation means that matter is not created or destroyed. Matter is not created. So we can't make atoms. Law of conservation, not conservations. Law of conservation. Matter is not created and stored. So I'm going to start with the chemical reaction NaHCO3 plus HC2H3O2, and that yields NaC2H3O2 plus H2O plus CO2. So we have two reactants. So I'm going to write reactants, and that's what goes in to a chemical reaction. And then I have products, and that's what is made. What is made in a chemical reaction. So this symbol here, the arrow, we read as yields. And that just kind of means that's what it makes. It's a one-way, it's like an equal sign that only goes in one direction. So, so I know that the same thing on one side has to be on the other side. So let's take a look. First, I have 1 sodium here and 1 sodium here. So I have, if I were to have a balance, if I drew a balance right here, whoops, I didn't draw it very straight, that's okay. So if I have 1 sodium here, then I would have to have 1 sodium on this side. Let's see, what other elements do I have here? I have hydrogen. I have 1 hydrogen here, 1 hydrogen here. Looks like I have 3 here. So 3, 4, 5 hydrogen. 1, 2, 3, 4, 5 hydrogen. And I'm just going to draw them out visually just to kind of help me see. So now I have 3 here and 2, so that's also 5. 1, 2, 3, 4, 5 hydrogen. Now let's see, what about carbon? Let's think about carbon. It looks like I have 1 carbon here, 2 here. So that's 3 in the reactant side. And I have 2 carbon here and 1 there. That's 3 on the product side. So I have 3 carbons on each side. And then what about oxygen? Let's look at oxygen. So I have 3 oxygen here and 2 oxygen here. That's 3 plus 2 is 5. And then I have 2 there and 2 there. That's 4 plus 1 more here is 5. So indeed, this equation, because it has the same number of each element, same number of each element on basically before and after the reaction, we can say that it is balanced. And that's why I have it on balance, though I should have made it a little bit more straight. So that's a balanced equation. Now we have, when we're looking at chemical formulas, we have a couple different things looking two different numbers that we're looking at. So if we have this, say this other equation, let's say we have PbNO3 2 plus 2Ki. Now, so if I have this equation, or sorry, this formula right here, then that's telling me that I have one Pb, which is lead. I have one of these. I have nitrogens. I have one here in the parentheses, but I have two of everything that's in the parentheses. So I could imagine it like this. I could have a Pb, one Pb, and then I have basically an NO3 on this side, and I have and 3 O's on this side. And not that you would need to know exactly how they're set up, but you could visualize this so then you could see that there are 2 nitrogens, 6 oxygens in this compound. And because there's nothing out here, I only have one of these. But now over here, I have a potassium and an iodine together. And but I have 2 of them, right? So here's one and here's one. I have 2 of them. So there's 1, 2. And so that's telling me that there are 2 of that compound. So when in balancing equations, or even when you're not balancing, when you're looking at chemical formulas, in a chemical formula, the subscript tells us how many of each atom or element, how many atoms, I should say, atoms of each element. And then the coefficient tells us how many molecules of that compound you have. So that gives us a little bit. We've covered a fair amount now of all the things that we need to know about atoms and the periodic table.